I want to introduce today's speaker. That is David Poulin. He's a professor of physics in Sherbrooke in Quebec in Canada. He headed the quantum information center there, and he co-founded recently a new institute, Quantic, in Sherbrooke. He studied in Waterloo in Canada. After that, he went to Australia as a postdoc, then to Caltech, and then he returned to Quebec, where he's been like a professor since. He's a charismatic scientist and speaker, and we're glad that he accepted to come here to give this lecture. Welcome, David.
Thank you, Matthias. Thank you, Matthias. Thank you, everyone, for showing up. It's a beautiful sunny day today, and I'm surprised that so many of you decided to spend an hour or 2 hours listening to talks on quantum mechanics. So for those of you who were at the Physics Cafe, there were very lively discussions about why we should be excited about quantum computers, what they might be useful for, how they might be built, and so on. In this talk, I want to do something different. I would like to kind of get to the very bottom of quantum mechanics and explain why it is so different. Okay? So my goal here today is that you can all walk away. You won't understand how quantum computers work, what they're useful for necessarily, but you will be convinced, I hope, that they are very, very different from the computing device that we have so far. Okay, so you've all heard the sad news this morning, the passing of Stephen Hawking, and it is hard to talk about quantum information without mentioning him in passing, because quantum information is about taking quantum physics to an extreme control in this case. But Stephen Hawking has pioneered the study of quantum mechanics and information theory in extreme conditions. So he was interested in black holes. And black hole evaporation is really something, at the edge of physics. But it is a puzzle that combines information theory and quantum mechanics. So certainly his legacy has contributed to quantum information, and more indirectly, myself and maybe a few other people in this group, in this room, are what you might want to call academic descendants. So Stephen was the PhD advisor of my PhD advisor, so this is another way in which he's probably had an influence on our field. So we want to talk about information processing, so we need to talk about computers. So here's what you might call maybe one of the early computers. It's a Babbage machine. It's a mechanical computer built about two centuries ago. And here is a computer at my home institution. It's called Mammoth Parallel. It's a supercomputer, you would call, and it's hard to read these numbers, right? This is 1,000, million, billion, so I guess 8 trillion operation per second. And it has a memory that's 50 trillion. Now this computer is being decommissioned as we speak because it's kind of it's out of date. Supercomputers are now much more powerful. This is about 10-year-old, okay? So no one uses it anymore. And how did we get, from this device to this device, or more generally in the modern age of computers from the 60s or 70s, what we've been observing is that roughly every year and a half, the computing power doubles. Okay, so what I mean by computing power, the processor gets faster, you get more memory, you get more RAM. Sometimes this does not translate to the user because everything you do gets more expensive as well. But the computer chip gets faster. And this is called Moore's law. Moore's law is not a law of physics, it's an observation. Okay, it's just an empirical law. And a lot of this is due just to the size of the component. If you shrink the components, the electronic components, well, you know, information has to travel on smaller distances. Everything can be faster when it's smaller. So shrinking down the components is really a big part of getting computers faster. And just to get an idea of the scale, here's a human hair. It's about 50,000 nanometers. Here's a virus, 100 nanometers. Here are some components. So the scale here is 100 nanometers. Okay, so we're able to build things that are, you know, tens of nanometers. Okay, and not far down, what's the next thing on the scale is an atom. Okay, so that's like, it's not too far below. So obviously, Moore's law can't just keep on going because you can't build stuff out of atoms that are smaller than atoms. Okay, so at some point, this is going to stop. And in fact, you can, following Moore's law, you can make a prediction, and this is going to kick in pretty fast. Okay, we may already have entered the era where Moore's law is stopping. Okay, because the components are too small. Now, I could say, well, at this point, quantum mechanics kicks in, and that's what quantum computers are about. But that's not right. I hope that I will convince you today that quantum computer is not just the natural continuation of Moore's law, just the same but better and faster, but it's radically different. Why is it radically different? In terms of computation. So for a quantum information scientist, there is no difference between this that you may recognize, like first generation of PC. You may have bought one of those in the early 80s. This is a supercomputer, and this is an abacus. Maybe some of you have played with this. You can do arithmetic with this. So as far as we're concerned, there's no difference between them. They're kind of the same device. Why is this? Well, the idea is that each of them operates by combining elementary transformations. Here's an elementary transformation, the OR gate. The OR gate takes as input 2 bits and outputs a single bit, and the output is a 1 if the first bit or the second bit is a 1. So here's the truth table. Okay? So you could have an AND gate where the output is a 1 if the first and the second bit is a 1. And you need a handful of these, and then you can start combining them into circuits like this. Okay? So now here I've drawn different gates, so you recognize the OR gate maybe. Well, this one doesn't have OR gates, but it's made of a few elementary gates. And this circuit, it might be hard to see, but it has different input ports. Some are labeled A and some are labeled B. And if I put on the A input port, I put this bit string, which represents the integer 23, and this bit string, which represents the integer 19, at the output, I will get the integer 42. So this circuit, and you could go through the circuit bit by bit, just apply these rules, and you could check it for yourself that it actually adds number. Okay? So I've taken something very simple, combined it into a larger circuit, and I can do some non-trivial operation, and then I could start building bigger and bigger circuit that do all the things that you know a computer can do. So from this perspective, whenever you have to do a calculation, like adding these two numbers, whether you do it on this machine, or this machine, the number of operations you need to do is the same. Of course, you might be able to do one operation per second on an abacus if you're kind of skilled. And this one maybe does a few thousand operations per second, while the one in the middle does trillions, as we saw. But it doesn't change the fact that the number of operations is the same regardless of the computer that you're using, right? It's just that one computer is faster. So quantum mechanics, quantum computation is motivated by this question. Do physical laws admit different, fundamentally different computational models? So can a given question, a given problem, be solved using fewer elementary transformations? Okay? And this is what we will see, that a quantum computer is not equivalent to any of the other computational devices because it uses the laws of quantum mechanics. Okay, so it uses essentially a different set of rules. And by using these different set of rules, it is able to do some computation. It is able to accomplish some tasks using fewer steps. Okay? This is what so my goal here is to explain to you how these rules are different. And I guess it's not surprising that when you change the rule, things can change substantially. Like if you're playing chess and all of a sudden you say, no, the king can just do whatever he wants. It's not the same game. Same thing with computation. Okay, so before I explain to you how surprising and counterintuitive quantum mechanics is, well, let's first agree on our intuition. The common sense that we all share. So as you may have guessed from my accent, I'm not from around here. I'm from Quebec, and in Quebec, the most important thing after quantum computation is ice hockey. So, so I will illustrate, I'll just use hockey statistics, and I hope that you will all kind of, arrive at the same conclusions as I do, because this is just like basic common sense. So, Montreal used to be the best hockey team. We used to win the Stanley Cup like every second year, but this is almost before I was born. The last cup we won, I think, is in '93, and we've been, it's been a pretty miserable team. So this is the best year I can remember. It's 2008. So we had two goaltenders that year. Yaroslav Alak, he had 56 wins and 34 losses. I've removed the ties just to keep the discussion simpler. And this was the second goaltender, Carey Price, 13 wins and 25 losses. Okay? So I've drawn little histograms here. So the top bar is the number of wins, and the lower one is the number of losses. Okay? So, I guess we all agree that, he's a better goaltender than that one, right? So let's try to quantify this a little bit. You could ask a question like, what's the probability of winning if you know that Halak is the goaltender? Well, it's essentially, it's proportional to the height of this bar compared to that one, right? So mathematically, let's just write a little bit of math. The probability of winning, and this line here just means given that. So the probability of winning, given that Halak is the goaltender, is something like 56 because he had 56 wins, divided by the total number of games that he played. Okay? So if you do the math, that gives you 62%. So 62% odds of winning if it's this goaltender. Now let's do the same with the other guy. The probability of winning, given that Price is the goaltender, would be 13 divided by 13 plus 25, and that is roughly 34%. Okay, so that kind of quantifies our intuition that he's a better goaltender than he is. Okay, so as far as I can tell, at the beginning of a game, the coach has to decide who's going to be the goaltender. And as I've analyzed this, and I think it's a coin toss. Okay, so every game, coach tosses a coin. So 50% probability is going to put this guy, and 50% probability is going to put this goaltender. So given this, I'd like to know what's the probability that they will win. That's a strategy. You flip a coin, and you either put one goaltender or you put the other goaltender. Well, common sense would say, well, it's going to be the average of these two things. Do you all agree? Right? That's common sense. And indeed, mathematically, that's kind of a theorem. The probability of winning is the probability of having one goaltender, so the probability of having halak, times the probability of winning given that it's halak, plus the probability of having price times the probability of winning given that price is the goaltender. And if you do the math, it's 48%. Graphically, you might introduce a graph and just say, look, I just add up these things, right? And I see, yeah, it's you know, slightly more winning than losing, but just by a hair. Everyone agrees with this? Common sense, right? Okay, now let's try to do a quantum experiment that reproduces this common sense. So I'm going to need an electron gun. I need something that fires electrons. If you run electricity through a piece of metal, the metal will heat, and eventually it might fire electrons. Okay? So, you know, from that point of view, a toaster oven is like a source of electrons. Okay? It just fires electrons. Now, if you actually want to run the experiment I'm going to describe, I would not advise using a toaster oven because you actually need electron with a fixed velocity. Okay? And you could put a filter, and there's a way of building a velocity filter using a magnetic field, but I'm not going to go into this. I'm going to assume that this thing just fires electrons at a fixed velocity. Okay. So in front of that source, we've put a wall, and we've punctured 2 holes in it, or slits. And behind the wall, we have an electron detector. This is something that just tells you where, it takes a picture of where the electron lands. Okay? So, and we've carefully placed a toaster oven so that roughly half of the time the electron will go through the upper slit and half of the time they will go through the upper slit. I'm not going to pay any attention whatsoever to the electrons that don't make it through either of the slit. Okay? These are just blocked. Okay. So you might want to think about this process as the coach who just flips a coin. Either the electron is going to go through the upper slit with 50% probability, roughly, or it's going to go through the lower slit. Okay? Good. So now we want to do exactly like we did with the hockey statistics. We want to accumulate statistics about each goaltender. Okay? So we want to put one goaltender in front of the net for a couple of runs, accumulate statistics, and then do the same with the other one. So let's do this. So let's block one of the slits and just see what are the statistics if I know that the electrons go through the upper slit. So you should think about this as what's the probability of winning given that I know it's one of the goaltender. Okay? So let's do this. Let's just start firing electrons again and again. So we just detect them on the screen again and again and again until we get like something that looks like this maybe. Okay? And that gives us kind of reliable statistics. We might want to draw a bell like this and say, this is roughly what the probability looks like. Okay? So you should take this as meaning that it's very unlikely that you'll find an electron here, and as you approach this kind of, this thing that is exactly lined up, this is the most likely place, and then it decreases again. Okay? The exact shape doesn't matter, but it's some kind of a bell shape. Okay, so now we know the probability of landing at some position x, given that the electron went through the upper slit, and we know it went through the upper slit because we blocked the other one. Okay? All right, so now we can accumulate statistics about the other slit. Same story. So we're able to estimate what's the probability of landing at some position x, given that the electron went through the lower slit. All right, so now what do? Exactly like in the hockey game, I start flipping a coin, and I remove the blocker here, and now the electron, can go through either slit. Okay? So the slide moved a bit too fast here, but I hope this is what you all guess. Is that what you would have guessed? Why? Because, well, we had a bell over here when the electron goes through the upper slit, and we had a bell-shaped curve here when it went through the lower slit. Now it can go through one or the other, so we should just average the probabilities. That's common sense. Okay? So this is no different than saying, same mathematical formula. the probability of landing at some position x is the probability of going through the upper slit, which is roughly 1/2, times the probability of landing at some position x, given that it's gone through the upper slit. And that was this bell shape. Plus, same thing with the lower slit. Okay? So let's look at experimental data. This is this screen here, and I hope that you can see that there are little white dots. So this is after 10 electrons were fired. So 10 is not enough to get good statistics. So let's just fire more electrons. So here's after 100 electrons. Hard to see anything. 3,000 electrons. 20,000. 70,000. Okay? It's not this double bell. What we see is something that looks like this. So our common sense fails. Okay? It does not behave like hockey statistics. In fact, it does not behave like anything you've ever seen. Let's try to digest this a little bit. So let's focus on this point here. Okay? When we block the lower slit, so when we force the electron to go through the upper slit, sometimes we saw electrons landing at this position. Okay, so there was a non-zero probability of landing at this position, given that the electron went through the upper slit. Now, whenever it was, sorry, I'm going to do this again. Sorry, I'm going to stop using this remote. When we blocked the upper slit, there was also a finite probability. Once in a while, we would see an electron land at this position. So think about this position as like the winning position, right? You'd like to see electrons at this position. When the electron goes through the upper slit, you can win. When it goes through the upper slit, you can win. Now you give it more options. Choose the slit. You can go through either one or the other. And what you see is that you cannot win. Okay? You cannot land at this winning position if you're given the option of going through either the upper slit or the lower slit. So I hope that this is making you uncomfortable. Okay? Because you shouldn't be kind of happy about this. Right? This is not normal. So what's the deal here? How can that be? Well, I don't know. How can the electron even know that the other slit is open? Right? I mean, the electron is like a point-like particle. It follows a trajectory, and if most of the time it will hit the wall, but once in a while it goes through a slit. But then it has to tell itself, this other slit was also open, therefore I must not go at this location. Right? It's crazy. Electrons don't do things like that. So you'll hear things like people will say, well, the electron went through both slits at the same time. That's the only, it did not go through one slit or the other, because our common sense, everything we know, our logic would tell us that you need to see this double bell, but we don't see it. So you will hear people saying, it goes through both slits at the same time. The electron at a given time is at two positions at the same time. Okay? Mathematically, we will say that, we'll call this a quantum superposition, and we'll say that the electron has an amplitude of being in the upper slit, which is equal to its amplitude of being in the lower slit. And I'll get back to this. Okay, but, I mean, I said that the electron is at two positions at the same time. So let's test that, right? No one believes me, so let's run an experiment. Let us put two detectors. If the electron goes by one slit, one of the bells will ring. If it goes through the other slit, the other bell will ring. So, all right, I'll send one electron, and hopefully the two bells will ring, right? So let's try it. Now, if you do this experiment, either one of the bells will ring every time. So the electron really goes through one slit or the other. Okay? But look at this. You also change the outcome of the experiment. You no longer have this interference pattern, you get the double bell. So if you want to see an electron being at two positions at the same time, it won't happen. It will either be at one position or the other, and then you can apply your common sense. Okay? And it works. So this is very frustrating. If we attempt to observe a quantum superposition directly, we destroy it. We destroy the quantum effect, and therefore, we can use our hockey statistic kind of reasoning to analyze this experiment. It works. And this is called the collapse of the wave function. Let's see. Right. So where you turn a quantum superposition into like just probability. It's either here with 50% or there with 50%. Okay. So these experiments are very old. I mean, this is things that people realized at the very beginning of quantum theory, and it's about a century old. And for decades and decades, these kind of things have been puzzling physicists and philosophers. What does this mean? What's the meaning of this? And you could say that quantum information science is a paradigm change where people stop asking these questions. They said, well, this is weird, okay? This is counterintuitive. These are systems that do not obey our logic, okay? Let us stop trying to explain what this means, but try to do something with it, right? It is weird. It obeys different laws of probabilities, different laws of logic, and computation is all about probabilities and logic. So if we build computers out of these systems, maybe the rules will change, and indeed they do. One of the examples, is cryptography. We heard about this during the physics cafe. So cryptography is about trying to communicate without being eavesdropped. Okay, you want to protect yourself against eavesdropping. So let's say that I want to transmit. And all the transmission is done with zeros and ones. So you encode your message in zeros and ones. And whenever you want to transmit a zero, I will use this triple slit device, and I'll use the two upper slit, just like in the previous experiment when I want to transmit a zero. And if I want to transmit a 1, I'll just move the toaster oven to this location here, okay? And the receiver, it's not working very well. So this is to transmit a 0 to transmit a 1. So if an eavesdropper wants to determine whether you're sending a 0 or 1, they will need to listen. But as I just shown to you, whenever you eavesdrop or listen or try to measure a quantum signal, you will disturb it. And indeed, Bob will be able to notice this and just tell his partner, stop sending information, we're being eavesdropped. Just abort the con. So it is impossible to learn any information about the transmitted signal without changing it. Okay? And that's the basis of cryptography. Quantum cryptography does not use toaster oven and things like this. They actually use photons instead of electrons because photons travel in optical fibers. They also travel well in free space, so it's a much more convenient system. And we heard during the Physics Cafe, I'm explaining that modern crypto system, like the one you use when you over the internet, rely on some mathematical assumption about the hardness of solving certain problems. While here you have a crypto system whose security is guaranteed by the laws of physics. Like if this system is well implemented and you manage to crack it, it means that quantum mechanics is wrong. Now you might, whether this is better than the math problem is up to you, I guess. And so the scheme was proposed by Charlie Bennett and Gilles Brassard in the early 80s, and you can now go and buy a device that does this. So these are just two terminals that you buy, and you hook them up with an optical fiber, and you have your quantum crypto system. Okay? So before I explain quantum computers, I just want to introduce a little bit more math. So we kind of have the basic ingredients because we've talked about probabilities, and quantum mechanics is some kind of generalization of probability. So whenever you assign probabilities, the first thing you need to know is what are the set of alternatives. So we call this configuration space. So, for instance, Halak and Price, these were alternatives, the two goaltenders. Or, upper, lower slit, these were alternatives. What else did we have? We had the position of the electron on the slit. It could be anywhere between minus infinity and plus infinity. These were alternatives. The state, so if you want to describe a quantum system, you will assign an amplitude to each of its possible configuration. What is an amplitude? An amplitude is much like a probability, right? If you wanted to describe a classical system, like the goaltender, you'd say, well, there's probability this, it will be this goaltender, and a different probability to the other goaltender. If you want to describe a quantum system, you'll just replace the word probability by amplitude. There's this amplitude for that, and this amplitude for that. And you just go over all the options, and you assign each of them an amplitude. So amplitudes are much, much like probability, except that the amplitude can be either positive or negative. And the probability, of course, can only be positive, right? If you ask me, what's the probability that it rains tomorrow, and I say -5, doesn't make much sense. So a probability has to be a positive number, while an amplitude can be a negative number. But at the end of the day, if you run a physics experiment, you want to predict the outcome. At the end of the day, it's all about predicting outcome. So at the end of the day, you want some probability. You want to say, I will measure this thing. What are the odds that I get this and this and that? So to turn an amplitude into a probability, you square it. Okay? As you may know, if you multiply negative numbers together, the minus signs cancel. Okay? So whenever you square a number, you're guaranteed to get a positive number. So I assign amplitude to the different configuration of a quantum system, and if you want to know, if you're just about to do an experiment and you want to know what's the probability of each of these outcome, you just square the amplitudes. Okay. So we could say that in the double-slit experiment, the state of the quantum system, while it was going through the slit, it had an amplitude 1 over square root of 2 of being in the upper slit, and an amplitude 1 over square root of 2 of being in the lower slit. And if you want to turn these into probabilities, you need to square. So you'll get a probability 1/2 that it goes through the upper slit, and a probability 1/2 that it goes through the lower slit. So it makes sense, right? So far, it doesn't look like we've changed much. But let me show you why this is important. Okay, so now we have assigned amplitudes to the system going through the upper slit and going through the lower slit. But now we're interested in the amplitude of finding the system somewhere on this detector. So let us use the same rule that we used with probability, right? I said the probability of a gain was the probability that Halak was the goaltender times the probability of a gain given that it was Halak, plus the probability that it was Price times the probability of gain if it is Price. Let's use exactly the same rule, but just replace these probabilities by amplitudes. So the amplitude of landing at some position X on this board is the amplitude of going through the upper slit times the amplitude of landing at position X given that you went through the upper slit, plus the amplitude of going through the lower slit times the amplitude of landing at some position X given that you've gone through the lower slit. Okay? So we're just copying here the rule that we used for classical probabilities. Okay, so now I've computed my amplitude, but I'm about to do an experiment. I want to know what's the probability that the electron will be detected at some position. So I need to square this quantity. Okay? So if I want to turn an amplitude into a probability, I need to square it. Okay, here's something you need to know about squaring. if I take 3 plus 2 and I square it, that's like 5 squared, so 5 times 5, that's 25, right? Now, maybe like if you're trying to do a quick guess, you might say, oh, that's 3 squared plus 2 squared. That's not the right answer, because 3 squared is 9, 2 squared is 4, so 3 squared plus 3 squared plus 2 squared is 13. It's not 25. Okay? So you got to be careful. So the right way to do it is to say it's this one times itself, plus this one times itself, plus this one times this one, plus this one times this one. You get these cross terms, okay? They're very important. And if you do it, I mean, you get 9 plus 4 plus 6 plus 6, and, right? And that gives you 25. It is not the same as squaring this one plus squaring that one, okay? Very important. So now let's apply this to our amplitude calculation here. So the probability of landing at some position x will be, so first it's this term squared, so that's 1/2 times the amplitude of landing at some position, given that you went to the upper slit, squared. Well, that's something that we've measured experimentally, right? When we forced it to go through the upper slit, we've measured this, so we know what this is. Then you get plus the same thing with the second term. And this is something that we've also characterized. If that was the end of the story, we'd get this double bell. Okay? But we forgot the cross terms. So now we're not at 25, we're at 13. So how do we get at 25? We need to add this term times this term, and this term times this term. But here's the catch. Whenever you take a number and you square it, whether the number was positive or negative, you get a positive number. But when you multiply two different numbers, one of them could be positive, the other one negative, and that would give you something negative. Okay? So while these are guaranteed to be positive, these can be negative. Okay? And this is how you can get some cancellation. Okay? This is why you could have something that was possible if you go through the upper slit, and it was possible if you go through the lower slit, but it's impossible if you have both options. You can get cancellations because of this rule. Okay? And we will say that you have constructive interference when both of these things have the same sign, so they will add up. And we'll say they have destructive interference when they have different signs, and in that case they can cancel and give you, a vanishing probability. Okay, so now that we understand how the magic works mathematically, we can start building devices out of these systems. So, I can say, well, this double-slit system, let me make a bit out of it. So if it goes through the upper slit, I'll just call this a 0. If it goes through the lower slit, I call this a 1. Okay, it's a two-state system, so that encodes a bit. Right, one particle, one electron in this case encodes a single bit. So to specify the state of this one electron, I need to assign an amplitude to 0 and an amplitude to 1, or if you prefer, an amplitude to being in the lower slit and an amplitude of the upper slit. But once I know how to build one of these quantum bits that we call qubit, I know how to build an array of them. And now I have an n-qubit system, and it's going to encode n bits. Something like upper, lower, lower, upper, upper, lower would just translate into 0, 1, 1, 0, 0, 1. So I can encode bit strings with n electrons. And if I want to specify the state of this n-bit quantum system, I just need to assign an amplitude to each possible configuration. Here's an amplitude that all the bits are in the state 0. Here's an amplitude that all but the first one are in state 0, and so on. And if you count, there are 2 to the n of those. Okay? So the state of a quantum computer, an n-qubit quantum computer, is determined by 2 to the n of these amplitudes. So you already see something exponential here, and that tells you that trying to simulate an n-qubit quantum system on a classical computer would require, if you do it the brute force way, and that's kind of the only way we know, it would require just a gigantic memory. Okay? So you can't simulate a quantum computer on a classical one because it requires a big memory. And by the way, 2 to the n, by the time n is something like 500, is more than the number of atoms in the universe. Okay, so it's a really big computer. Okay. So, all right, now we have like a quantum memory, quantum bits, but we want to manipulate these quantum bits. Now, one thing I can do in this double slit experiment is put a piece of glass in front of one of these, in front of one of the slit. And if I choose the size and the density of this piece of glass just very accurately, the effect of it can be to turn this positive amplitude into a negative amplitude, okay? So you might want to think about, well, what would be the effect indeed would be that because I've changed the sign, every time I had constructive interference, I will now have destructive interference and vice versa, right? Because whenever things added coherently, now they will just subtract. So you can guess that on this interference pattern, it will just change accordingly. Okay? What was possible becomes impossible. So you might want to think of this piece of glass as some elementary gate. It has no classical analog. It's not, putting a minus sign in front of a probability is not something you can do classically. But it's an elementary transformation which is allowed on a quantum computer. It has no classical counterpart. Don't even ask me what it means. It doesn't have any meaning, not with words that you and I are familiar with. So here's how a quantum computer would operate. So you take a bunch of these qubits, and initially you prepare them in some simple state, like maybe you have just equal amplitude to all configuration. That's something that's very easy to prepare. And then you just send it through a network of these elementary gates. Okay? So you should think about this exactly like we assembled a circuit, and this is how we call it. We call it a quantum circuit. And this will change the initial amplitudes that were red into the final amplitudes that are now blue. And the trick, if you're a quantum programmer, you're thinking about what marble to put at what position in such a way that when you do the final measurements, and as you know, the probability of getting a certain measurement outcome is just the square of these amplitude. Well, you want to put the marbles just at the right position in such a way that the good answers interfere constructively and the bad answers interfere destructively. So you get more probability of getting a good answer than a bad answer. Okay? So this is what programming a quantum computer is all about. Now, you might ask, what kind of problems can we solve with this? So here's a little puzzle. So 15 is 3 times 5. So anyone can answer this? Just speak up. 2 times 13. I think I heard the answer. 5 times 17. Okay, we'll have fun. Okay, this problem is pretty hard. And you see here, I had an 11-digit number. Okay? And as I keep growing this number, I keep adding digits, the problem gets harder and harder, as far as we know. Okay? We don't have any algorithm that can solve this problem as you keep increasing. Well, we do have one, but here's its complexity. So here I've written, this is the number of elementary transformation that a classical computer needs to do in order to solve this problem as a function of the number of digits. Okay? So it's a nasty formula, but let's apply it. Let's just see what this formula predicts. So let's assume, just for sake of argument, that this here took a microsecond on a computer. It's probably less than that, but it doesn't matter. Okay? A microsecond. Well, according to this formula, the same algorithm could solve this one in about 500 microseconds. Okay? So you see, I've just gone from 2 digits to, 11 digits, and 500 times slower. And what if I try a 600-digit number? Well, with that scaling, that would take about the age of the universe. Okay? So this formula, as you can see, is an exponential, and exponentials are nasty, okay? Peter Shor found a quantum algorithm, so he found a way that you could program a quantum computer, which would lead to a factoring algorithm. And the factoring algorithm had a different formula, okay? So, you know, if to the trained eye, oh, this is really different, but it doesn't look so different. It's got a few different symbols, but let's just see how this example would change with that new formula. So, in fact, you know, quantum computers are actually likely to be much slower, tremendously slower than classical computers. Okay? So what took a microsecond is I mean, it could take a minute as far as we know, okay? But it's going to be much slower. So, okay, that doesn't look very good, but it's the way it scales, okay? So if you go to the 11-digit number, it would take only 2 seconds. And if you go to this 600-digit number, it would take 16 seconds. This is what this formula predicts. Okay? So the number of operation is really radically different. It's not exponential, it's a polynomial. So you could ask me, how is this happening? And you know, I could tell you, oh, you know, the quantum computer just tries all possible solution. You know, is n equal to 1 times 1? No. Is it equal to 1 times 2? No. Is it equal to 1? And just, you know, list all the possibility in parallel because, you know, the bits can be in superposition. You could do all of them at once, and then you just pick the good one. But this is a pretty lousy explanation. This is not how a quantum computer operates. It's much more subtle than this. And if I'm kind of cornered and you force me to answer this question, here's the best I can do. Okay? So you have your problem, and a computation is about finding a path from the problem to the solution. And the streets are made of elementary transformations. Okay? So here's a first step. Okay? So I hope that you can see I've just taken a small step in the direction of the answer. And this step could be an OR gate or something like this. Okay? And then I'll just go on and take small steps and slowly make my way from the problem to the solution, combining a bunch of elementary gates. And as you can see, it's taking a bit of time. All right, finally. So this is classical computation. Quantum computation, as we saw, can make elementary transformation that have no classical counterpart. They defy our intuition, but they can be performed in the lab. And once you understand this, that you can do these transformations that put like a -1 in front of a probability, well, then maybe you can find a much shorter path. Okay? So it's not about having a faster computer. It's about having a computer that has access to different streets. A little bit like the chess game that I said. Okay? So if you ask me, well, describe the computer halfway through the computation. What are the bits? You know, what are the bit value in the computer? I can tell you things and like, well, all the possible bit values are in the computer, I mean, I can try to say things, but we don't have words to explain what's going on here, okay? We do have very, very reliable mathematics. I can give you a mathematical expression. I could give you the amplitude halfway through, okay? But understanding this defies intuition. So I would say that quantum computers can accomplish certain tasks more efficiently because they follow different rules. Rules that defy our intuition, but are mathematically very well encoded. Okay? So there's no question about the mathematical foundation of quantum theory. This is something very well established. It's been tested. Everyone believes it's right. But it does defy intuition. So given this, I think the most interesting questions are, can they be built? This is a grand challenge, a scientific and an engineering challenge. We're making baby steps along this way. And what else can we do with them? Okay? And we're having a workshop this week here at the Aspen Physics Center to try to make progress on some of these questions. All right, so I'll leave you with that. Thank you so very much for your attention.
Thank you, David. And before we come to questions, I want to remind you that next week's lecture is not here, but next week's lecture is at the Physics Center. The week after, it will again be here. With that, are there any questions?
I see one in the back.
In the back? Yeah.
Right. Yeah. So the question is whether I believe that a quantum computer can be built, or whether it's like nuclear fusion. My personal belief is that it can be built. I mean, it is a tremendous challenge. The more you know about it, the more it becomes, the more you understand all the different layers of challenges that are that have to be met before we have a working device. So it's a tremendous scientific project. But the only reason I have faith that it will be built is that if I think back in the 40s and I say, can this be built? You know, the answer is there's no way. And I bet you, if I were a physicist in the 40s, I would write theorem proving that you cannot build this, right? It's just the amount of innovation that went into building something like this is unbelievable. Quantum computers might require even much more, but I think they can be built. Now, if they will be built is a different question, because we need a good reason, okay? It might be it's very likely to be a multi-billion-dollar project, hundreds of billions. So you need a pretty good reason. And it's hard. Well, we heard about applications. There's a website that lists about maybe order 50 algorithms for a quantum computer. Here are 50 things we know how to do. And this is kind of the quantum computer app store. And so you could say that's not a lot, you know. The app store for my phone has more than 50 apps. But it did not have more than 50 apps before there were phones, okay? We don't have quantum computers. It's kind of surprising we already have 50 applications. But we definitely need more application. And maybe the last comment I can make is there is a possibility that it cannot be built for some fundamental reason, okay? But we do have a very rigorous theory proving that it can be built. If the laws of physics are the way we think they are, it can be built. So if there is a fundamental reason why it cannot be built, that will also be very exciting, because we will learn new physics. It will mean that there's something fundamentally new that we did not know about physics. Yes?
So using this example you have up here, I'm going to ask when I use the word power, I'm going to mean electrical power, quantum, microwatts, whatever. So I'm imagining going down one pathway which takes significantly longer, and the other pathway that takes shorter in time. When we think about standard computing today, we get things done faster in time. We usually do that by running the machine faster, using more electrical power. If I'm looking at those two different pathways, should I also imagine that the pathway which seems more efficient in time, I think is the time you illustrated here, should I also believe that it's potentially more efficient in electrical power as well, the consumption of the machine,
Right.
the performing operations?
Yes, so the question is, well, there's often a trade-off where faster machine require more energy, more power, more electrical power. So the question here is whether, like if we compare these two paths, one is shorter, but is it consuming more or less power? That is, I mean, it's an important question. I don't think we are currently at the stage of answering this question, but I can give you a few different pieces of answer. First of all, if you look at the quantum computer itself, it's operating at extremely low temperature, okay? Therefore, the kind of intrinsic power consumption is minimal, because you're not, you know, if you want to perform an operation on a classical computer, you need to flip like a little droplet of spins, and these you have dissipations in these systems and so on. Here we're almost at zero, absolute zero. So everything is done in a almost dissipative-less way. So the intrinsic power consumption is lower. However, there's a bunch of things that go around the computer. First of all, the fridge. Okay, so you have a dilution fridge, and you know, right now we have dilution fridge. I'm not an experimentalist. I don't know exactly how much power they consume, but it's more than, you know, a regular fridge. We put just a couple of qubits in there, like tens or, yeah, a few tens, and it's heating quite a bit, so you need to throw quite a bit of power just to keep the thing cold. Now, if you imagine scaling this up to billions, well, the power consumption for just the cooling might be a very important aspect. The other aspect is that the way we envision building quantum computers now, there will be a lot of kind of side classical processing going on. This is essentially for error correction. So the quantum computer will be noisy, so we will perform checks periodically on the system, and these checks will have to be processed by some classical computer and then feed back to kind of keep keep a good control of the quantum computer. This is also likely to consume a lot of power. We might even want to put this classical processing stage in a dilution fridge just to decrease the amount of power. But in terms of raw numbers, I don't think we are at this stage now where we can give a precise answer.
But wouldn't you say that if the classical computation would take the age of the universe and quantumly takes a minute,
you
can make an estimate?
Of course, yes. Yeah, I interpreted the question like, you know, okay, yeah. So surely, as you scale the thing up, eventually, you know, by any metric, it's better to use the quantum computer. That's for sure, because you're looking at an exponential versus a polynomial.
How do you know that entanglement has an effect of the path?
Right. So entanglement is a special property. Oh, sorry. The question is, how do we know that entanglement has not affected the path? So entanglement is a very special feature of quantum theory. Well, maybe I should explain what entanglement is. Let's see. Well, okay, to explain what entanglement is, I need to back up and explain what correlations are. So let me try to do that quickly. So, okay, correlations. Correlation is when you have, say, two objects, and by looking at one, you learn something about another object. I can give you an example. So, you know, I went skiing this afternoon, so I was a bit rushed before I came here. So I dressed very quickly, and I don't remember the color of the socks that I put on. But I am pretty sure they're the same color. Therefore, let me look at my right sock. It is beige. I bet you the left one is beige. Okay? I'd be willing to make a bet. Okay? So I've looked at one place, and I learned some about the other place. But let's suppose, on the other hand, that I'm the kind of person that only has beige socks. Okay? Then by looking at this sock, I wouldn't learn anything about that one, would I? So correlation require lack of information. If you know everything, you can't have correlation because you already know everything. You can't learn something by looking at something else. Entanglement is this very special feature of quantum mechanics, that you can know everything there is to know about the system, and yet you have correlations. Okay? So this is a very kind of important, deep property of quantum mechanics. And it's also, well, it's a two-sided coin. So we love entanglement because we use it, and it shows up in a lot of protocols and in computation. But I suppose what you were alluding to is that the system can become entangled with undesired system. Okay? And change the answer, absolutely. So if along the way, let's say you're computing with these electrons, and something like a little photon comes and scatters on the electron. Now the electron is entangled with this photon. And as a result, you would lose this precious coherence, just like when the bell tells you which path the electron took, you lose the precious quantum. So it's the same idea, but it doesn't need to be a bell. It could be just a single photon. So this is indeed the main obstacle to physically building these devices, because on the one hand, you want to have qubits that you can manipulate, so you want some kind of connection to them. On the other hand, you want them to be completely shielded from everything. That sounds like a catch-22, right? And there's a lot of effort to kind of solve this problem, but the main solution is error correction. So we are able, a quantum computer, a universal quantum computer, will be running some error correction code, and even if there's this entanglement occurs once in a while, it can tolerate. And there's this thing called the threshold. We know that if something goes wrong every roughly 100 or 1,000 operation, then we can error correct. If it happens more often, we can't. So the current race is for the experimentalists to get these devices more accurate than this threshold. And once we're there are software methods that kick in to protect the computation.
I just think you don't know entanglement has occurred.
So the question is, I don't think you know that entanglement has occurred. This is a very good question. You don't want to look at it directly, but trust me, we know. I mean, and many prominent scientists have made the same objection in the early days of quantum computers, but we found ways around this. Yeah.
This question goes on my flawed understanding is, why can't you build a virtual quantum computer and pretend like the quantum event is happening and then do your calculations based on it?
So the question is, why can't you build a virtual quantum computer and just so by virtual, I presume you mean like one that would live on a classical computer. So have a classical computer simulate a quantum computer. Indeed. So to answer this question, I would need to go back a few slides where I said, if you have n qubits, a quantum mechanical description of this requires 2 to the n amplitudes. I cannot store this. I cannot store this on a hard drive. By the time I reach, in fact, a few dozens, it's already impossible. So simulating like 30, 40 electrons is out of reach for the world's biggest supercomputer. It's already out of reach. And this gives us a ballpark estimate. How big of a quantum computer would be useful? Well, more than 50 qubit already we could not simulate it. So that gives us like a lower bar.
There was one question back there.
Correct. 4. Oh, sorry. Yes. So when I showed I mentioned that you needed a few elementary classical gates like the AND and OR, and then you get what we call a universal gate set. So you can implement any transformation with those. And the question is there a similar result for quantum computers? And the answer is yes. In fact, there's a universal gate set that has just 4 transformation. Am I missing one? 4 or 5? So anyway, this for the expert. But yes, there is an elementary set of transformation. What I did not show here is that you need something that couples 2 qubits together also. Because if you only have these transformations on 1 bit at a time, you cannot generate like multi-qubit transformation. So you need 3 single qubit transformation and 1 that couples them, and you're done.
We have time for one last question, if there's any.
In the picture you showed, Henry, the interference between the electron source and the double slit, you described the process of observing any of the slits results in some error or generation. Does that result a similar process that is sensitive to noise? That's one of the reasons analog computers went away.
Yeah, so the question is, I showed on the slides with the bells measuring the position of the electron, I showed that such measurements had a great impact. You kind of lost all the quantum features when this occurred. So given this, it seems like quantum systems are highly sensitive to noise and maybe more like analog computers, which indeed, analog computation is an extremely powerful model. So by the way, analog computation just means that you have continuous variables as opposed to just bits, real numbers. And this is an extremely powerful computational model, but it has been dismissed as a computational model because you cannot stabilize it. Okay? You cannot prevent errors from building up in an analog computer. So you can maybe analog compute for a little while, but eventually you get rubbish. So is quantum mechanics the same thing? And this is, again, an important question, and a lot of people thought it was because you have these real amplitudes and so on. But it happens to be kind of halfway between continuous and analog, because indeed you have these amplitudes, and you can perform continuous transformations on these amplitudes. So the set of transformations that are allowed on a quantum system form a continuum. So far, this sounds exactly like analog computation. However, when I measure a bit, when I measure a qubit, the only possible answers are 0 or 1. So it's kind of halfway between analog and classical, and in just the right way, so that there's a theory of quantum error correction and fault-tolerant quantum computation, just like von Neumann had a theory of fault-tolerant classical computation, right? You can classically compute despite having errors. You can quantum compute despite having errors as well. The overhead is not too great. Indeed, it's logarithmic. So if you have a computation that scales like n, then if you want to error correct it, it would scale like n log n. So it's not too bad.
Thank you, David, again for the lecture. Thank you all for coming.